trigonometry from scratch. Let's say that I am a Greek mathematician in ancient Greece, and lately I've been getting a lot of questions about triangles. For example, someone might know what an angle of one of a triangle is, and maybe they want to know one of the sides, or they know two sides and want to know another side, and they come to me to get the answers to all these questions. And most of these questions are about right angle triangles. Either directly because someone's working in architecture, so lots of things involve vertical walls against horizontal grounds, or let's say you're a lighthouse and you know what angle you are to the horizon and you want to see how far away a ship is given that you know how tall your lighthouse is. I mean, that's really just a right angle triangle in disguise. And if you have an isosceles triangle, you can split that in half and then you'll get two right angle triangles. And most triangles you care about, you can find a way to slice that up into right angle triangles. So my plan is, well, I've got some time on my hands during the day, so why don't I just come up with a big table of all the triangles that I can think of, and I'll write them down, and I'll use a ruler to work out what the lengths of the sides are, and a protractor or a compass to work out what the angles are, and I'll just write them all down in one big table. So anytime that someone comes to me asking a question about a triangle, I can just look it up in my table, and then I can tell them whatever missing pieces of information they want to know. And if I don't have the triangle in my table, I'll work it out with a ruler or something like that, and then I'll just add it in. So I write down a couple of triangles in my table, getting the picture of the triangle, then the three angles, and then the three sides. So I kind of collect a bit of data, and it's not long before I kind of realize some patterns emerging. So firstly, I don't need to write down I've got 90-degree angles, because these are all right angle triangles in the first place. And secondly, I can always work out what the second angle is based on the first one, because it's always going to add up to 90. If the interior angles of a triangle is always 180 degrees, and we know one of them is 90 degrees, then the other two are always going to add to 90. So I keep going with a new triangle, and this one's 20 degrees, and I could work out that the other angles will be 70 and 90, but I don't need to add them to the table because I can just derive that. So I keep going, and soon I realize I've written down a triangle that was quite similar to the first one I wrote down. All three sides are exactly the same as the first one, just scaled up by a factor of 2. And if I look at the angle, it's quite clear that the two angles of the two triangles are exactly the same. So I can go ahead and just cross out that new triangle because it's not really giving me any new information. I can just derive that information from the first triangle. So let's explore what we can do with this concept of scaling up triangles. So I can get the same triangle before, the angle 36.9 degrees, and in this case the longest side, the hypotenuse, is like 20 meters long. So let's go back to my table, and I've got a slightly smaller triangle than that. The hypotenuse in mine is 5 meters long. And all I need to do is just scale it up to be the same size as the triangle that I care about, in this case the one with 20 as the longest side, and then I can just work out what my other length should be. So what were they in my smaller triangle? That's right, so it was 4 and 3. Okay, so that means going back here, the hypotenuse is 5, and then the adjacent is 4, and the opposite is 3. So we're just going to scale that up, and that's going to be 12 because we're timesing it by 4, and then the 4 becomes 16. So if someone comes to me with a triangle and I've got that same angle in my table, then I'll just look at the hypotenuse of my triangle, see what factor the difference is, and then scale all the sides up accordingly. But then I run into trouble when the hypotenuse of this new triangle that I care about is something that's hard for me to kind of divide into. So if I've stored in my table a hypotenuse of 5, in order to scale this up, I need to know what 17 divided by 5 is, and I'm not very good at division. Well, maybe what I should do is, all the triangles that I'm storing in this table, I should just make their hypotenuse some length that easily divides into things. And nothing divides into things better than the number 1. So now I can go and record, if it's 36.9 degrees and the hypotenuse is 1, then the adjacent side to that angle is 0.8 meters, and the opposite side is 0.6. So now my life is very easy, because 17 divided by 1 is just 17. So if I want to know what the length of the sides are of a triangle whose hypotenuse is 17 meters, I know that my adjacent side of my original triangle is 0.8 meters, to scale it up, I just times it by 17. Same with the opposite side. It was 0.6, I'm scaling up my triangle by 17, so I get 0.6 times 17, which is 10.2. So given what I've learned, I can go back and start this table again. It only needs 3 columns, the angle, the opposite side, and the adjacent side. I don't need to store the hypotenuse this time, because it's always going to be 1. Another benefit of having a hypotenuse of 1 is that we can see the opposite and adjacent side as basically just being percentages. If it says it's 0.34, it means that it's just 34% of the hypotenuse, whatever the hypotenuse happens to be. So if I have a triangle of an angle with 20 degrees, and the hypotenuse is 30, I can look at my table and say, okay, well, when the angle is 20, then my adjacent side is, for example, 0.94, or 94%. So I just need to find out what 94% of 30 is. I've got my answer, which in this case, let's see, what is that? 28.2. Another thing about having the constraint that all of the hypotenuses of these triangles is just 1 is that for every triangle I write where I'm pivoting the angle slightly, what I see is that the upper right corner ends up tracing a circle. So let's draw a unit circle. It's not my best, but it's not that bad. And each of the triangles that we've been making here will fit inside this circle because the radius is 1 and the lengths of our hypotenuses is also 1. So for example, here we've got a triangle with an angle of 30 degrees, and so the point on the circle is just the length of the triangle and then the height of the triangle as the x and y coordinates. So we've got 0.5 as the height and 0.87 as the length. So now I have a new idea. Instead of writing down all these mappings from an angle to the opposite side or the adjacent side in a table, I can just graph them out on a plane. So here my horizontal axis is just my angle, which will go through 90 degrees, 180, 270, and then 360 when the circle completes. And so looking at the first point, my height is going to be 0, and then as we get towards 90 degrees, it's going to end up being 1, because the unit circle's radius is 1. Then we keep going, and by the time we get to 180 degrees, we're looking at we're looking at 0, and then we loop around more, and eventually we get down to 270 degrees, where it's now exactly -1. As we continue, we're going to get closer to our original position, which is where we just have a flat triangle to our right, and so it's back to 0 again. And when you plot each of those out, you get this smooth curve like so. And this vertical axis is just telling us what is the length of the opposite side of the triangle as a percentage of the longest side, because the longest side is 1. So if our opposite side's length is 0.5, for example, when we're at 30 degrees, then we're looking at a 50% size compared to the longest side of the triangle. And because that's a bit of a mouthful, I'm just going to call this sine of theta. I can also go back in the other direction. So say that I know that I've got a triangle where the opposite side's length is 94% of the length of the hypotenuse. I can just trace that to the corresponding point on the graph, and I can see that that must have an angle of 70 degrees. And the way I'd write this down on paper is that I'd say that sine of my angle, say 30 degrees, is equal to, well in this case, it is 50%, or 0.5. Going back in the other direction, if I want to say, okay, what angle is it that gives me an opposite side, which is half the size of the hypotenuse, or 0.5? And I'd write that as sine -1, or inverse sine of 0.5 is 30 degrees. Okay, so we've looked at the opposite side. Let's look back at the adjacent side, our horizontal sides. So we'll just write down the same axis again with 90, 180, 270 and 360 degree values of our angles. So we start off with a angle of 0, in which case we're just a collapsed triangle where the adjacent side is of length 1 because there's no height to it. And then when we get to 90 degrees, we're looking at the exact opposite. It's squashed vertically, so it's 0. Then at 180 degrees, we're at -1. And then coming around to 270 degrees, we end up vertical again, so we're 0. And then we're back to where we started at 360. And this is the length of the adjacent side as a percentage of the longest side. That's a mouthful, so we'll call it cosine theta. So we can do the same thing as we did with sine and say, for an angle of 30 degrees, how long is the adjacent side inside this triangle? So looking at the graph, it's about 87%, or 0.87 exactly if your hypotenuse happens to be 1, which it is in all these triangles we're drawing on the circle. So we'd say cosine of 30 degrees is 87%, or 0.87. And we can go in the reverse direction and say that the inverse cosine, or cos -1, of 0.87 is 30 degrees, meaning, you know, that's the angle required for the adjacent side to be of that length. So now anyone can come to us with a triangle where they know what the angle is and what the hypotenuse is, and if they want to know the other two sides, well, we just say, look, we don't know about that triangle, but we do know about this triangle where the hypotenuse has a side of 1. And for that case, whatever the angle is, the opposite side is sine of the angle, and then the adjacent is cos of the angle. And then we can scale it up by just timesing everything by the hypotenuse, and then we'll know what the lengths of the opposite and adjacent sides are. So as an example, let's say someone has a triangle with a 30-degree angle, and the hypotenuse's length is 6. We can just take our 30-degree angle triangle, where we might know that the sine of 30 degrees is 0.5 and the cos of 30 degrees is 0.87, and then we just scale that up, times everything by 6 because that's the length of the hypotenuse, and then we end up with the same triangle in terms of shape, but now it's 0.5 times 6 being 3, or 0.87 times 6 being 5.22? Yeah. And just looking at this, it kind of makes sense. Like, if sine of 30 degrees is 0.5, then it says that the opposite side is going to be 50% of the hypotenuse when we're at 30 degrees. So if the hypotenuse is 6, then obviously our opposite side is going to be 3. Likewise, the cosine of 30 degrees is 0.87. So if our hypotenuse is 6, then we would expect the adjacent side to be 87% of 6, which is about 5.2. So we end up with 3 and 5.22. And we've made this very easy for ourselves. Their triangle has a hypotenuse of h, ours by design has a hypotenuse of 1, so we just scale by a factor of h to get the numbers that we want. So far so good, but what happens when we have a triangle where we don't know what the hypotenuse is? All we know is the angle and the length of the adjacent side. And maybe we want to know what the opposite side's length is. Well, what it would be nice to have is to know for all triangles where the adjacent side is 1, what is the length of the opposite side. And then we could just scale it up by, in this case, a factor of 10, and let's say we've just denoted this as, you know, f of theta. We scale that up by a factor of 10, we can end up fairly easily knowing what the length of the opposite side is, just by saying, okay, well, it's, you know, the triangle's got the same angle, 30 degrees, we've times everything by 10, and then so our adjacent side will be 10, and our opposite side is just 10 times whatever that number is, which is some function of, in this case, 30 degrees. Well, all these other triangles we've been making have existed sitting inside this unit circle, because the length of the hypotenuse is 1. But we now care about the triangles where the adjacent side is always 1, which means it'll be triangles that as you pivot this angle, they'll end up getting just taller and taller and taller as they touch the tangent of the unit circle. So we can do what we did with the other two functions and say, for each angle I can think of, how long is the opposite side? So at an angle of 0, obviously there is no height to that triangle, so we're going to be at 0. And we know that when the angle is 45 degrees, both the adjacent side and the opposite side are the same, so it's going to be 1, meaning 100% of the adjacent side. And as for 90 degrees, as we approach 90 degrees, our triangle just gets infinitely tall. And we can never really end up with a triangle if our angle is 90 degrees, because then we've got two 90-degree angles and we've got two parallel lines, which means we can't form a triangle. So we end up with an asymptote. Now, for completeness, if you continue this curve, it actually ends up looking like this, which is a little bit weird looking, but I'll explain in a bit why it takes on that shape. So in a nutshell, what we've graphed here is the length of the opposite side as a percentage of the adjacent side. But as with the others, that's a bit of a mouthful, so why don't we just call this the tangent of theta? Because we're talking about triangles that sit on the tangent to the unit circle. So going back to our original problem here, we want to know what tan of 30 degrees is. So we just look at the graph and it's looking like it's about 0.57. And now we've come up for a better name for our function here, and we're going to call it tan of theta. So tan of 30 degrees, we've just checked, is 0.57. So when we scale up this triangle, it's going to be 10 times 0.57, which is 5.7. Now, I have a feeling that there is a relationship between tan and sine and cos. So I'm just going to have a look at the two different triangles that we've been talking about. The first one is the one that sits inside the unit circle. The other one kind of has the opposite side sitting on the tangent line. So on the smaller circle, the adjacent side's length is cos of theta, and its hypotenuse's length is 1. And also its opposite side is sine of theta. But then looking at the larger triangle, the opposite side's length is tan of theta, and obviously the adjacent side's length is 1. So just drawing this out again, we've got our triangle with a hypotenuse side of 1, and we've got cosine theta and sine theta as the other two sides. And then the other triangle we've been working with is the one that has a adjacent side's length of 1, and the opposite side's length being tan theta. So what if we tried scaling from one of these triangles to the other? So let's divide all the sides by cosine of theta. So on the adjacent side, when you divide something by itself, that's going to equal 1. And then on the opposite side, we're going to end up with sine theta over cos theta. And the hypotenuse will just be 1 divided by cos theta. Now, the important thing is that these two angles are the same, and the adjacent side is the same, so the opposite side must be the same, meaning tan theta equals sine theta over cos theta. So now we can go back and look at these graphs that we've drawn and just confirm that everything still makes sense. So when sine starts, it's at 0 and cos is at 1, so 0 on 1 is 0. When sine is 1, cos is 0, and you can't divide by 0. And then it's 0 and negative 1, which makes 0, and then negative 1 is 0, which again, you can't divide by 0. So that's why tan theta ends up taking on the shape that it does. You also know that whenever sine and cos are both positive, tan will also be positive. And whenever one of sine or cos is negative, tan will be negative. So now we can solve pretty much any problem that we want to involving a triangle when we know the angle. We've got our triangle with the hypotenuse of 1, and then the lengths of the other two sides being sine theta and cos theta, and we can just scale that up by a factor of h to work out what the unknown sides of our triangle is. So because these two triangles are equal in size, we know that the opposite side is the hypotenuse times sine of theta, and the adjacent side is the hypotenuse times cosine of theta. Now, to solve problems where we don't know what the hypotenuse is, but we know what the adjacent side's length is, we've got this other set of triangles where the adjacent side's length is 1, and then the opposite side's length is tan of theta. So with these, we just scale that up by a factor of a, and we end up with the opposite side being a times tan theta. Okay, so what do we do when we have a triangle where we know what the two shorter sides are, but we don't know anything about the angle and we want to know what the longer side is? Now, our three trusty formulas aren't that useful to us because they all depend on knowing one of the angles. Well, this will seem weird at first, but bear with me. If we have a triangle of lengths A, B, and C, we can just draw 4 of them kind of stacked side by side to form a larger square. Now let's work out what the area of this square is. So Looking at the larger outside square, we know that the length of each side is just a plus b. So therefore the area is just going to be a plus b times a plus b. And if we go and multiply those two things together and expand out the terms, we end up with a squared plus 2ab plus b squared. Now the other way of writing this area is to say, well, we've got four triangles, so that'll be 4 times a half ab, plus the inner square, which is just going to be c squared. So that's 2 times ab plus c squared. Now these two areas are just the same number, so we can remove the 2ab term from both of them, and we end up finding out that a squared plus b squared equals c squared. And I would call this Jesse's theorem, but I'm pretty sure a guy named Pythagorean beat me to it. Okay, so back to our problem. We want to know what h is, which we'll call c for now. So we know that 8 squared plus 6 squared equals c squared. So what's that? 64 plus 36 equals c squared, which is 100. And if 100 is c squared, then c equals 10. So we've got our answer. Okay, so now if you ask me anything about any right angle triangle, as long as I've got 2 pieces of information, I can give you the thing that you want to know. So we've got a squared plus b squared equals c squared, opposite equals hypotenuse times sine theta, adjacent equals hypotenuse times cosine theta, and the opposite equals the adjacent times tan theta. We also worked out that tan theta is just sine theta over cos theta. So now, as the ancient Greece town mathematician, I am fully capable of answering any question anybody has about any right angle triangle.